Welcome to Brain Vision.
Hi everyone, so what we have is air going through a changing diameter pipe. It enters at a temperature of 65 degrees C and a pressure of 200 kPa, and it exits this pipe at 60 degrees C and a pressure of 175 kPa. We know that the air loses heat at an amount of 3 kilojoules per kilogram, and that the ratio of the inlet to the exit diameter is 1.4. What we're asked to find is the inlet velocity and the exit velocity. So the first thing we're going to do is just write down our assumptions. We're going to assume that this is a steady state process, so nothing is going to be changing with time. We're also going to say that changes in potential energy are negligible, as is anything related to work is also negligible. And we're going to assume that we're dealing with an ideal gas with constant specific heats. So first thing we're going to do is go ahead and find the properties of our gas. So we know our gas is air, so the gas constant is going to be 0.287 kilojoules per kilogram Kelvin. And we're also going to see that our specific heat for constant pressure, Cp, is going to be 1.005 kilojoules per kilogram Kelvin. And this is a quantity that is pertaining to the Cp at room temperature. Next, we're going to define our system. We're going to define the pipe as our system, and we're going to define that as our system because the mass is crossing the boundary of that control volume. So when we do our mass balance, we'll see that the m dot coming in minus the m dot coming out is equal to the m dot, or change in m dot of the system. Recall that we are assuming that this process is steady state, so this change in mass of the system is going to be 0. Therefore, we can say that m dot in is equal to m dot out. Now, if we go ahead and write out what m dot is, we can see that this basically means that rho A1 V1 is equal to rho 2 A2 V2. What we can go ahead and do is for rho, we can use the ideal gas law and actually go ahead and plug in the geometry as well for the areas. And we'll see that this equation actually becomes P1 RT1 pi D1 to the 4th over D1 squared over 4. Go ahead and correct that. Times velocity 1 is equal to P2 RT2 pi D2 squared all over 4 times V2. As you can see, there are certain quantities here that are common between both sides, so we can cancel them out. So the r, the pi, and the 4. And what this gives us is a relation that looks like P1 D1 squared V1 all over T1 is equal to P2 D2 squared V2 all over T2. Next, what we're going to go ahead and do is do our energy balance. Now, similar to our mass balance, we can say that the rate at which energy enters the system minus the rate at which it leaves the system is equal to the total change in energy rate of the system. As we assumed before, this is a steady state process, so this is going to be equal to 0. Therefore, we can say that the E dot in is equal to E dot out. Now, we can actually break this up into its constituents and say that E dot in is equal to H1 plus V1 squared over 2. So this is energy due to enthalpy and velocity that is coming in. And then we have that set equal to the energy leaving due to the mass, to the enthalpy, energy due to kinetic energy, but also the heat that is lost. So that's going to be Q out. And what we can do is go ahead and rewrite enthalpy in terms of that's constant specific pressure heat, so that specific heat capacity, and then also temperature as well. So we can see that H1 is equal to CPT1, and go ahead and say V1 squared over 2 is equal to CPT2 plus V2 squared over 2 plus Q out. Now what we're going to do is actually we're going to go ahead and assume that the inlet diameter is going to be 1.4 meters and the exit diameter to be 1 meter. And recall that we had a relation relating these inlet and exit diameter ratios to be 1.4. So what I'm going to do is go ahead and plug that into our equation for our mass balance equation, and that's going to look like this. Remember, our mass balance equation is P1 over T1 D1 squared V1 is equal to P2 over T2 D2 squared V2. So we actually have all these quantities except for V1 and V2. And when I plug this in, this looks like 200 over 388 times 1.4 squared V1 is equal to 175 all over 333 1.0 squared times V2. So this is equation 1. And next we have, remember we have the equation 2, and this is going to be coming from our mass balance. And recall that equation 2, after we plug in for all of the variables, is going to look like so: 1.005 times 338 plus V1 squared all over 2, 1 over 1000 is all equal to 1.005 333 plus V2 squared over 2, 1 over 1000 plus 3.3. Now, what you can see here is we have two equations with two unknowns, V1 and V2. Now, these are two equations, two unknowns. We can simultaneously solve these, and what we get is the solution for V1 and V2. We see that V1 is equal to 29.9 meters per second, and V2 is equal to 66.1 meters per second. And that's our final answer.